Oh, it is. Good. So before we get started, I want to advise you, I'm going to do questions and answers probably up front here at the end. I won't do them interactively with the mics. I have a ton of content, and I'm really worried about finishing on time, and I don't want to keep anybody here late. If I do finish early, that's great. We'll have a chat up here. But I'd like for you to hold your questions if you wouldn't mind, because I do have literally a ton of content to go through. So I'll tell you a little bit about myself before I get started. I'm, in technology terms, what's known as ancient. I've been in technology more than 25 years. I'm a developer. I released my first code into the public domain in 1989. Posted it on a bulletin board system, thought I was all cool. It was a little game called Minor VGA. And in this game, you would get a shovel and a pick, and you would go down underground and dig at the dirt and find gold and silver and bring it back up to the top. And I abandoned that project and put it in the public domain. And about 15 years later, a company called Mojang made Minecraft and sold it to Microsoft for $2 billion. And in Minecraft, obviously, you take a shovel and a pick, and you go underground, and you dig at the dirt, and you find gold and silver. So have you ever given up on a project too soon and lost $2 billion? Yeah, I have. So I can tell you it's not much fun. Funny thing about releasing software into the public domain, though, you get emails on it 30 years later. People want to port it to the PlayStation. They want to port it to DS. They want to run it on a browser in HTML5. I don't know. What can you do? So I have the privilege of being in professional services at AWS for the last 2.5 years. And I live in San Francisco, which means all of my customers are big tech companies in the Bay Area. And I go into the companies, and I'd be willing to bet that everyone in this room within the last 24 hours has used technology products from one of my customers. In fact, it's almost guaranteed. Unless you're living under a stone and have no technology, then why are you here? You're using my customer's technology. And when I go in with these customers in a professional services role, I'm working directly with their engineers and their architects. And so I have a kind of a unique perspective in some of the boundary pushing that they're doing in terms of serverless, and in particular, ways to optimize serverless at scale. Because these are not small customers. We're talking billions of transactions, billions of invocations, a month. And it's no small feat to make this stuff work, make it work reliably in those type of environments at scale. I've learned a ton from my customers. Hopefully I'll be able to share some of that with you here today. Okay, so why are we here? I guess probably you all know about this thing called serverless, and you all may have heard of Lambda. Lambda is, if you looked at the tweets this morning, the number one mentioned AWS service in all the reInvent tweets. Despite all the machine learning we've been talking about, Lambda is at least 5 times ahead of every other service mentioned on Twitter. It's amazing. In terms of executions, we're up in the trillions of invocations a month, and growing, at a ridiculous pace. How many of you currently, where are we on our Lambda journey? How many of you run Lambda today? Okay, I'm not surprised. So if I asked that question a year ago, it would have been 3/4 of the room. If I asked it 2 years ago, it would have been half the room. If I asked it a year before that, it would have been a few speckled people, right? Anyone who says they have 5, 10 years of experience with this technology is lying, because it hasn't been around that long. So if I can learn it and master it in a few short years, so can you. So can your people. And frankly, it doesn't really matter, because all going to change within a few years anyway. That's the nature of cloud. That's the nature of technology. So today's focus is going to be on the compute side of Lambda. I will talk about some of the other serverless services like SNS, SQS, step functions, API, gateway. But I'm going to focus on optimizing Lambda. And Lambda is essentially a compute platform for most of the serverless that we do. By the way, raise your hand if you deploy your Lambdas using a production-style code pipeline like Jenkins or serverless.com. Okay, and raise it again if you have automated testing of your Lambda when you deploy it using those automated pipelines. Yeah, so a lot fewer, right? So the funny thing about Lambda, serverless in general, we tend to think of it as a shortcut. I don't have to do all the things I used to do. I can just put stuff into production. That's great, except that whether it's serverless or not, it's still software engineering. So I'll come back to that later. But we tend to take shortcuts with serverless, and we tend not to think about scale, and it can really bite us. Oops. Okay, so you're probably all familiar with this model. A Lambda function has an event source. There's something like 30 plus sources in AWS now. So the obvious ones like S3, Kinesis, but there's some less obvious ones too. You can kick off a Lambda from AWS Connect by making a phone call. You can kick off a Lambda from an IoT device, a dash button. Every Alexa call, that every time you talk to Alexa, that's a Lambda function that's running. You probably already knew that. It's got 5 runtimes right now and more coming. And it's tightly integrated with all of our services. And most Lambdas also call third-party services, whether they're on the internet, they're some application you're running in your VPCs or in your data centers even. And so there's this ecosystem of an event hits the Lambda, and the Lambda talks to these other services. This should be review, I would think. So the anatomy of a Lambda function, there's 4 layers, basically. And I'll start at the bottom. The compute substrate. The compute substrate is ours. We own that. That's the hardware that Lambda runs on. We manage it. You don't have to know anything about it. How many of you heard the announcement about Firecracker? Yeah, pretty exciting. Most of you will never even look at Firecracker. The reason is because it's just one of the tools we use to manage our substrate. And there's no reason for you to touch it. You wouldn't actually be able to optimize your environment by going into Firecracker anyway. But I think it does show a commitment to the open source community. And the goal of putting it in open source is that more people will be able to contribute to it and find any security holes in it and help us improve it, and essentially make us more transparent so you'll know what's going on under the hood. The next layer is the execution environment. You do have some control here. The execution environment is how the Lambda got invoked. It is whether the Lambda has an ENI in your VPC. It is the environment variables that you've set. It's all the node packages that you've put onto the container. Then there's a language runtime. You can't really optimize that, so think about like a JVM. You can't optimize the JVM, right? It's the Java machine. Within other languages like Python, it's the binary. Go, it's the binary. And of course, at the very top of that stack is your function, and you can optimize your function. So I'll talk about really these 2 areas where you can optimize your Lambda functions. And it's not really, it's kind of intuitive that you can optimize your function. It's not intuitive to everyone that you can optimize your execution environment. So hopefully I'll show you some ways to do that. So let's start with the function. So every Lambda has three major components. There's an event that gets passed to it. There's a handler that handles that event. The handler has your logic in it. And there's also this context object. The context object is passed to the Lambda to tell it where it's running, what its timeout is, how much memory it's going to get. Most of the time, your business logic won't care about the context object. It's very rare that you'll need to even interact with a context object. Most of your interaction would be with the actual event that you got passed. But you can look in the context object to find out, for example, where your logs are going to go, what the destination for your logs are, what your timeout is. If you need to make a decision about whether to put something into a queue or process it right now, you may care about what your timeout is, and that may be variable depending on if you're in production or test, for example. So at the simplest event, let's say, tell me what the time is right now. You have an event source, like an API call, and you have a Lambda function, and that's the extent of your universe, right? And so what that looks like, this is a very simple function. I think it's looks like Python. Hard to tell sometimes. In any case, you've got some basically case structure at the top, right? So based on some parameter, some element of the JSON event, I'm saying I either go to function A or function B, and then the actual business application logic is contained in function A or function B. A very simple pattern, but that's pretty rare that you actually have that simple of a Lambda function. A more common scenario is an event hits a Lambda, and the Lambda interacts with a bunch of services and databases, right? It can interact with queues, it can interact with Dynamo, it can interact with RDS. And this is an example of that. So we'll decompose this sort of one step at a time. But just if you glance through it, it's got some initialization at the top. It's got a handler with some basic logic. And then it's got a series of functions, some of them tied to the logic, some of them tied to the initialization. So we'll start with this first initialization bit. What's the initialization doing? It's loading your libraries. It's getting a secret from somewhere, probably a database connection string, and it's actually making a database connection. Now, it's meaningful that that is placed where it is. If you put that inside the handler, that means it's going to execute every single time the Lambda runs. By putting it where it is, it means it's going to execute only when the container is initialized. So it will be persistent across multiple invocations of the handler. So the first time you run this, it runs it from top to bottom within the same container. The second time you run it, it only runs the handler. And the third time and fourth time, et cetera. Containers are persistent. They'll stick around for 5 to 15 minutes. We keep them cold in case you need them. And if you've had 10 concurrent Lambdas running, we've got 10 frozen containers waiting for the next 10. And if you've had 10,000, we've got 10,000 frozen waiting for the next one. So we'll talk a little bit about what that means and how you can optimize using that. The thing to think about is it's a single event per execution environment, a single event per container. And there's no way to really target a particular execution environment. It's not like there's sticky sessions. Like the next one's not going to go to the same execution environment. So there's no point in having anything persistent in the execution environment anyway. Execution environments are reused, so you don't want to load absolutely everything into them, right? You don't need to execute everything, not every code path. So let's go back to this example. I've got my function A and my subfunction B at the bottom there. Only one of those code paths is likely to be executed in any given scenario. If the function A at the bottom is 90% of the traffic, and the container executes 75 transactions and never sees B, it will never actually put a B into memory, right? So it's a lazy load of that. Let me go back. So don't load it if you don't need it. I think that should be obvious. But we'll come back to this idea of what belongs in the initialization of the Lambda and what belongs in the handler, because it really does affect all the performance of your Lambda. The next bit, let's look at this secret handler. So this seems like something you could manage in the deploy. Why would I need to do that at runtime, right? There's a couple ways you can manage secrets or sometimes application toggles, right? Environment variables such as dev, test, prod. So one way is to manage it using environment variables. That's what this one's using. And basically, environment variables in the Lambda environments are key pairs that get passed in at the time you create the function. And they are available very simply and easily with no heavyweight APIs. You can pull them right out of the OS environment. So in Python, for example, it's at the OS environment. In Node, it's process env. But the point is, you don't actually need any packages or any API calls to get that out of the environment variable. It's very easy, very lightweight. It's a very good place to store it if it's not going to be reused for other functions. You can also encrypt it. So what folks will do is they will actually encrypt the environment, let's say the connection string using KMS, put the ciphertext into the environment variable, and then on load, the Lambda will go and will make a call to KMS to decrypt the text, the blob. The good news about that is then you can use IAM to control access to that key and therefore access to that, the contents of that environment variable. It's also really good for, I think I mentioned dev test prod type of switches, changes in application logic. The other way to do it is systems manager parameter store. So the advantage of parameter store over environment variables, parameter store would be useful if you had multiple functions sharing a secret. Let's say you got 5 functions and 3 of them need access to the same database. If you needed a different database connection string across dev test and prod, and you did a different environment variable for each of them, that's 15 environment variables. By the time you do all that in your deploy code, it's probably simpler just to stick one entry into parameter store. And parameter store also supports hierarchies, so if your project has multiple secrets, multiple application flags, you can give access to a parent and it inherits the roots. Again, same idea of you can do plain text or you can encrypt with KMS. You can also do notifications. So if an environment variable is changed, you really have no way of knowing. But you can send SNS messages, you can do CloudTrail, you can do a lot of tracking on parameter store that you can't do with environment variables. It's also less brittle, right? It's a database, it's an API call as opposed to something that's done at deploy time. It can be tagged if you're doing build back or show back. And it's available directly via API. So on the right there, you can see some code that's actually making the call. The yellow code is the 4 or 5 lines of code you need to reach out to parameter store and get a value or a set of values. So it's not complicated to retrieve secrets from parameter store. So, and also notice here, we've put that retrieval of the secret outside of the handler. So once the container has the secret, the next invocation doesn't have to get it again. The next invocation doesn't have to get it again. The next 10,000 invocations, it doesn't have to go get it again. That's a good optimization. And you may have heard of AWS Secrets. So over the summer, the 2 teams got together and actually homogenized the API between parameter store and AWS Secrets. So if you're making a call, regardless of which endpoint you're making it to, it's exactly the same API. So for all intents and purposes, I use the 2 interchangeably. Secrets is actually a subset of what's available in parameter store. Parameter store has more capability, but Secrets has a smaller set of API, common API responses. Down at the bottom, one of the things we always recommend is get your application logic, your business logic, out of the handler. And for the reason I mentioned before, you're going to not execute every path for every transaction. And if a path never gets executed, it never gets loaded, right? It never gets put into memory, just sitting there. It's going to be faster and, more importantly, your handler itself will execute faster and load faster, and then it can lazy load whichever portions of the code it needs. So definitely, one of our recommendations is always separate the handler from the application logic. We also think it's pretty important to use Lambda functions only for transformative things. If you're doing something with the data, if all you're doing with a Lambda function is taking something off of an SNS queue and putting it in an S3, you're just moving an event from one place to another. You've become piping. And frankly, there's a feature that does that. You can drop SNS entries directly to S3. You don't need to write code to do that. So when you look at your code, look at what it's doing. If it's moving data from one place to another and not making any changes to the data, you probably should look at another way to do that. There's probably another pattern that would satisfy that without doing it in your code. I think the other thing, we talked about dynamic logic configurations. So if it does something different in dev than it does in prod, then don't build that logic into if-then statements or case statements in your handler. Use environment variables and manage it in your function, in the logic of your function. The other thing that's really important, the way we all used to build software is we would give our application, our giant, beautiful, monolithic application, access to all the data and let it sort out what it needed in the data. And it would do that usually with SQL, right? It would execute some crazy big SQL command. That's actually really an anti-pattern for serverless. What you want to do is really give events to functions, let them execute. If they need to reference data, then use a filtered set of data. Use a view that filters down what that thing actually needs. Don't have Lambda sitting there waiting while your database is executing SQL, right? And there's services to do that quickly. So I mentioned here query filters in Aurora, S3 Select, but there are ways to trim out the chaff and get just the wheat handed to your Lambda function. And it makes a big difference, because if your database is cranking away and your Lambda's billing, you're paying, and your customer's waiting. The other thing we talk about is no orchestration in code or no workflow in code. So if you were in the school of coding that I went to, you really wanted to build resilient code. You wanted to have a code that was bulletproof, so it would have retry logic right in the code. Like if something happens, wait for it and check it and make sure it's finished, right? And then once it's finished, move on to the next thing and then check that and make sure that's finished. I'm not saying you should abandon error handling. You just really don't need to do it in your code, right? Your code needs to be unifunction, do the thing, and then use another methodology to track retries and to track failures and to track error modes. You don't need to put that in your code. The reason, if you put it in your code, then you're inevitably waiting for the failure, right? So I kick something off, now I gotta wait 10 seconds, and maybe if it fails again, I gotta wait another 10 seconds. That's waiting time. Lambda's wasting money and time, and your customers aren't happy. So how could I get that out of my handler function? How can I get it out of my code and deal with it some other way? So if you're using one of our queuing mechanisms, most of them have some retry capabilities built in. I'll talk about those in a minute. But one of the easier ways to do it is with step functions. Who's used step functions? Okay, anyone using it to do retry logic for a Lambda? A few? Excellent. So step functions is a great way to get your retry logic, your orchestration logic, your workflow logic out of Lambda. So if you haven't used step functions are basically a workflow orchestration system, a management system with no administration. You don't have to do anything. It's nothing more than a YAML file that defines a workflow around your Lambda and defines what to do if something fails. And your Lambda can pass back custom failure codes to that, and you can build deciders in that are not code, they're just configuration that can route your workflow from one Lambda to another Lambda to a dead letter queue if it continues to fail. It can also manage parallel tasks, asynchronous tasks quite well. So when you're decomposing your microservices into nano functions, think about why you would want any type of error handling, back off, retry in your functions. Put it in the piping, put it in the orchestration environment. Don't put it in the function. The other one, this one's pretty controversial, by the way, so if you really object violently to this, I apologize. It is, even within our team, if you ask 3 people, you'll get 4 answers. But mono repos are the idea that I want all of my functions that support a given application. Let's say I've got 6 functions that support an application. I want them all in the same code repo with their infrastructure as code, so Terraform or CloudFormation or SAM or whatever. I want them all in one code repo. And the thinking behind that is I'll get a bunch of reuse, right? The problem with that is you have a permission problem and you have a social contract problem, because anyone who has access to one function has access to all the functions. And you have a social contract problem because I can go in and blow up your function by changing some infrastructure code, right? The other thing about it is the dependency footprint of functions is very different, right? So I've got one that accesses database. It needs packages to access the database. I've got another one that accesses, web encryption. So I need different set of libraries for that function. If I put them all in the same repo and I build them all into the same zip file and upload them to Lambda, then every Lambda is carrying a bunch of weight around with it that doesn't need to carry. It's not going to ever execute that code. Now, obviously, you can build separate packages, jar files, whatever, with only the dependencies that you need. But if they're in the same repo, the tendency is just zip it up and send it as a block. So the dividing line here is, if they share an event source, then you should maybe consider putting them in the same repo. So if they're both coming from S3 or they're both coming from an API call, then maybe they should be in the same repo. If one's coming from S3 and the other's coming from an API call, put them in separate repos. Make micro repositories for them. It simplifies permissions, it reduces the footprint of each one, and frankly, the reason we used to like mono repos is because deploys were very complex and hard. To build a code pipeline, you'd get a consultant in, or you'd sit for an afternoon with your head in your hands trying to build a code pipeline. Code pipelines today are 10-minute jobs. You can find code that'll spin you up a code pipeline for a repo in 20 minutes, not even, right? And you can have, I can have 100 repos, each independently deployable, and it costs me nothing because, frankly, you only pay when you do the deploys. It doesn't cost you anything to have the pipeline sitting there, right? They're pay per use. So I don't need a bunch of dedicated code. The other thing is, we used to build very complicated deploy mechanisms because there's dependencies in these deploys, right? Having more code pipelines means those are easier to manage and, frankly, less onerous because it's the same deploy mechanism for every function as opposed to a custom one for this one and a custom one for that one. And we talked a little bit about testing. If you put a bunch of functions in a single repo and you do a deploy and it deploys all of them, your test suite has to test them all, but really you only changed one of them. Why test all the rest of them? Maybe regression testing. So the advice is avoid mono repos. Have micro repos. You can combine them if they share an event source, and also be very mindful that you're not loading packages that you don't need. Dependency packages, I mean. Okay, so to recap on what you can do with your Lambda function, the first thing is minimize your dependencies. So another thought here, if I am going to do some HTTP requests, I load the HTTP request framework. It probably can handle every variety of header and every variety of parameter modification. It handle every type of cookie there is. Guess what? My incoming HTTP that I need to parse probably uses 2 of those. So why do I need such a heavyweight package? How about I strip things out of that package and get down to the 2 things I actually need? That's a useful tip. Use pre-handler logic strategically. So pick and choose what goes in the initiation and what goes in the handler. And I'll show you a way to get to that in a minute. Use secrets and use a deploy mechanism for secrets that depends on your scope. Single function, single application, single deploy mechanism, environment variables are the lightest weight thing you can do. But they don't scale when you've got multiple functions. They don't scale when you've got multiple teams working on the same code. So then you go to parameter store, secrets, AWS Secrets. Think about how reuse affects variables. So I had a customer, a very big customer actually, in the photo sharing space, and they had an application that did the minify, taking a long URL and making it a small URL. And they were doing it, billions of transactions. And they kept really overloading the database. Like, there wasn't that many transactions, and the database kept going crazy. And he says, look, I've only got 10,000 invocations, and I'm using 20,000 database connections. What is going on here, right? But what he wasn't thinking was, about 2 minutes ago, he had 20,000 invocations, and the database connection was in the header, right? It was in the initialization. So those containers were still sitting there. Those connections are still active, still available, in fact, for the next 20,000. So you got to think about where it makes sense and when it doesn't make sense to put something in the handler versus the global scope. We talked about concise logic. To the extent you can eliminate orchestration, you move it out into step functions. You should do it, workflow, and avoid mono repos. Essentially, if you can do it, it's the tendency, because of the way we were trained. Particularly if you're a Java developer, you're trained to make big, giant jar files, war files. It's an anti-pattern for a couple reasons, but the biggest one is the people get sloppy on the dependencies, and so you don't know what actually needs to be in there, and you just end up uploading everything every time, and you get these massive payloads. And remember, on Lambda, you pay for every byte, right? It's a very small amount, but you pay it if it's 10,000 invocations an hour, it adds up. So now we'll talk about the execution environment, the things that you can adjust there. It's separated really into two segments. So on the left is everything that we control. And that is, when we create a new container, we download your code. You actually do control that bit. How big is your zip file? How big is the code that you've given us? Is it only the things that need to be there? Have you made your function small enough, right? But for the most part, you can't actually optimize that at this point. And starting the execution environment, that's all on us. What you can control is bootstrapping the runtime and running your code, and then the actual handler beyond that. You can optimize that in a couple ways. You can optimize it function by function, or you can optimize it across an entire system of Lambda functions. And I'll be talking more about that as the slides go on here. The problem is, when you look at stats out of Lambda, duration, right? Duration includes everything there, particularly for a cold start, right? Everyone know what a cold start is? Raise your hand if you know what a cold start is. Okay, good. So duration doesn't really help, right? Like, how do I know how much of that is in my bootstrap and how much of that is in my code, right? It's too bad there wasn't some way, some magic wand that would let us introspect into the Lambda function and all the functions in an ecosystem and see where it's going. I don't know what you'd call something like that if you had such a tool, but I was advised, actually, before I came on stage, that if you were nervous about presenting, you should imagine your audience naked. I'm just saying, yikes. Wow. I admire that, though. I've never gone commando at a tech conference. I think reInvent, it would chafe. So it turns out there is such a tool. It's called Xray. And Xray, how many of you have used Xray? Okay. If you haven't used Xray, what Xray does is Xray inserts tracers into every HTTP call header in your ecosystem. So you have to tool it. You have to put a couple of lines of code, like the ones at the top, into your Lambda function. And basically, it can then create a service map of your application and all the calls going on in your application. Now, with Lambda, you kind of get it for free, because most of the services in the Lambda ecosystem, in the serverless ecosystem, are already including those tracer headers. And Xray can already visualize that for you. With other implementations like Elastic Beanstalk, EC2, ECS, EKS, you have to actually include a little bit more code. It's not difficult. You can tool anything that runs in the cloud on AWS practically to interact with Xray. And so if you take a look at that service map, it's showing you all the calls that were made. The green is a 200, the red is a 500, and the yellow is a 400 response. And more importantly, it's showing you the duration, the duration of each subcall in your system, and you can drill into those. So if I drill into one, I can look at the actual trace, and it will show me, for example, how long it took to cold start or restart the container. It can show me how long it took to get its IAM role, how long it took to get credentials, how long it took to get an ENI from your VPC. And you can see cold starts in here quite easily, actually. So if the top bar is the entire run of the Lambda, and the bottom two bars represent, the small blue one represents your initialization phase, and the other one represents your handler, your application logic. So from the time Lambda started, from the time the call came in to the time your handler started is the cold start, right? And you can optimize around that. So you can have more in your initialization phase as opposed to in your handler. If the mix looked the other way, you could take a look at it and say, well, maybe I can put more of that in the handler because it's wasting too much time on every call. So Xray gives you that capability to see into your Lambda functions and optimize the duration of every element of the ecosystem. So if you haven't used it, you should definitely try it. I wouldn't put it in production first. Put it in dev test. Use it there. Remember, though, in dev test, you get a lot more cold starts. In production, cold starts are the 99th percentile because practically your traffic keeps things warm, right? In dev test, you just release the code. It's never been executed before. You run it. Guess what? You're going to get a cold start every darn time. So if you use it in dev test, remember to execute it a few times and look for the cold start traces and ignore those pretty much. The other thing about it is if you do put it in production, you can sample it. You can create a sampling rule. So this one, the default rule says, show me every HTTP transaction. I want to capture everything. I want all the data. More data, please. But in production, maybe you only want to see the errors, and maybe you only want to see 5% of the errors, right? You can capture it by percentage. You can capture it by max Q. And basically, that data is sampleable in all of your environments, but you don't want to do detailed sampling in production at scale because you'll blow the doors off of Xray and slow down your functions. So Xray tells you what you can tweak in terms of your function. There's a couple other things in your execution environment that you can play with. The biggest knob, really the only knob you've got, is memory. How much memory do I give my function? How much is the right amount of memory? And if you say, well, I ran my function, it said the max memory it ever used was 50K, and I gave it 128 meg, it should be good, right? It never hit near the max memory. But remember that memory as the knob also controls CPU. So when you give it 128 megabytes of memory, you're giving it the absolute smallest sliver of a virtual CPU. And as you increase the memory, you get more CPU. It's a proportional timeshare on that system. And when you get to 1.8 gig, you get one whole CPU, right? So how do I determine, I guarantee you don't know today whether your functions are compute bound, network bound, throughput bound, memory bound. Very unlikely that you know that. So how do I resolve that? One way is to test it at various memory settings. That's actually what we recommend. Remember I talked about having that test suite earlier? It's really useful for this. So here's an example of a Lambda that we wrote to test this compute-bound idea. It basically calculates prime numbers 1,000 times for up to 1 million. And at 128 megabytes of memory, it runs for 11 seconds. And it's cheap, right? 128 megabytes times 11 seconds, 2.5 cents or something like that. But if I add a little more memory, it does speed up, but it starts to cost more. And I add a little bit more memory, it still speeds up, but it really starts to cost more. But look at the bottom one. I added enough memory. It now runs 10 times faster. So it only runs, it's 10 times the memory, but it runs 1/10 the amount of time. So the net is I get it running 10 seconds faster, but I'm only paying 0.0001 more. Now, this is easy for businesses to digest. Would you rather save a fractional penny, or would you rather have things running 10 seconds faster, right? Easy. There's no business person in the world who's going to say, no, save that fractional penny, right? And you may think, probably my stuff's not CPU bound anyway, right? But remember, we switched SSL certs from 1024 to 2048, and it's not double, because it's logarithmic, actually, the compute power to decrypt and encrypt. And a lot of your stuff is HTTP bound. So even if it snuck up on you, you may be CPU bound and not know it. I had a customer run something on EC2, cost him $1 million a month, run it on Lambda, cost him $150,000 a month. Added memory, ended up costing him $60,000 a month. From 150 to 60, more than half reduction by increasing memory, which is counterintuitive. I increase the memory, I should be paying more, right? And by the way, his performance went up like 15x. So there is a threshold at which it doesn't make sense, though. So unless your code is multi-threaded, you're not going to be able to take advantage of a second CPU. So when you get above 1.8 gigabytes, you get a second CPU. But if your code is not multi-threaded, it's not going to use that anyway, and so you'll see no performance improvement from the CPU perspective. For I/O bound, yes, you'll get more of the network and you get more of the backplane. It might improve. So be aware of the block there. The other thing you can do is you can control the execution model. So at the very top of the pyramid, usually you've got an API call coming in, right? And that's /order, /customer, /product, whatever. And that's synchronous. You have to respond to that in real time, and there's not much you can do to adjust that execution model. But below that, under the hood, you have some control. You could use a queuing mechanism. You can use a polling mechanism to feed events to your Lambdas in an asynchronous fashion. And I'll talk a little bit about what we call the iceberg, the Microservices Iceberg, and how you can use this below the water. The thing to think about this, the characteristics of each of these queue types is very different from a persistence perspective, a retry perspective, and I'll cover some of that. So, the one thing that people tend to overlook is actually just you can make a Lambda API call yourself. You can invoke your own Lambda. So the idea behind microservices is everything has to be behind an API, right? I'm going to create a microservice. It's going to have an API. It's going to have a / something. It's going to hide behind a load balancer. Technically, you don't need that. If it only has one function, and that's to do something asynchronously, you can actually just invoke it with an API call yourself, and you can pass it any event you want. This is really powerful. It's in all the SDKs, and folks tend to overlook it. The idea of a Lambda calling a Lambda is not intuitive. And definitely synchronously, it doesn't make any sense, because then they're both running, one waiting and one working, and you're paying for both. But asynchronously, the one that pulled it off the queue and gave it to the appropriate sub-Lambda is gone. It's gone, and you're only paying for the one that's actually executing. And what that looks like in code is 4 lines of code. Create a Lambda client and invoke the API and pass it context and a payload, basically. And then behind the scenes, we're managing the queue of that and the retries of that. So I talked about this Microservices Iceberg. At the top of it, you have a public interface. There's nothing you can do about that. You have a public interface. You got to provide that. But everything below, you can architect. So you're taking that microservice and you're breaking it into nano functions. The nano functions don't have to be just code calling code. You could implement a queuing mechanism there, or an SNS, right? And you can use any of the polling methods I described before within that universe, including just invoking asynchronously other APIs, other Lambda functions. We talk about gateways and routers. So the way to sort of choose where to implement it, if you have a single custom client, just fire off an API. You don't need an API gateway that's going to cost you money and slow your performance. if it's an in-region public, use API Gateway public endpoints, regional public endpoints. If it's an internal one, use private API Gateway endpoints to front it. No need for a custom interface. Maybe if you don't need a custom interface, maybe you can actually use a managed service, SQS, SNS. And discard uninteresting events. So again, much like we talked about on the database side, you've got a stream of events coming at your Lambda. Does the Lambda really need to look at all of them? Maybe there's a way to filter them before they get to the Lambda, so the Lambda is only looking at the ones that are useful to it, rather than filtering it inside the Lambda, right? And there are ways to do that. So S3 has event prefix, SNS has message filtering, SQS has something called attributes, or labels, sorry. You can filter things before they get to your Lambda, and therefore not have to execute the Lambda at all. So focus below the waterline and think of it as a software engineering exercise, not a serverless exercise. And give as much thought to the architecture beneath the line as you do to everything outside of it, like databases, persistence, et cetera. So the ways that you can optimize, I could probably spend another hour on these 6, and I don't have an hour, so I'll only talk about 3. The one thing that you must do is manage concurrency. And concurrency is important for a couple reasons. It's essentially, out of the gate, it's a shared pool. So these are the 3 models. In concurrency, if it's an API call or SNS, that means for every event, it's going to spawn a Lambda. If it's queue-based, that means that you're going to get pollers that pull batches off the queue. And if it's stream-based, that means you're going to be able to shard it across multiple shards. And each of those has a different, is optimized differently across these 3 aspects. So the reason it's important is your Lambda can easily become a DDoS machine for your database, right? If you put an SNS queue in front of a Lambda, and the Lambda spins up 3,000, 10,000 copies of itself, and each of them tries to do an insert onto an RDS database, you're going to blow that database up. Concurrency is real. You have to manage concurrency. The other problem is concurrency is shared. Unless you specify per function concurrency, it's shared, which means that one runaway rogue Lambda can eat up all the available concurrency in your account for a region, and then no other Lambda, any other Lambda, could run. So the main way you manage it is per function concurrency. And it acts as a reservation. So if I say 10,000 is the max number of concurrents for this particular Lambda, that takes it out of that shared pool. It gives it its own cap, its own limit. And so even if everything else goes to heck in your environment, that Lambda will get 10,000 invocations, up to 10,000 invocations. So you have to manage concurrency, and the way you manage it is a little different depending on which invocation method you're using. So if it's an API, the only way to manage it is your per function concurrency. If it's SNS, the only way to manage it is per function concurrency. SQS, you can manage that using batching. So when Lambda pulls things off the queue, it pulls off batches up to 10, for example. And with Kinesis streams, you manage it with sharding. So one function per shard. Persistence. So eventually you're going to push bad code and you're going to blow up your Lambda. Or something downstream is going to fail and you're going to blow up your Lambda. So the question for you is, am I going to lose data? Right? Am I going to lose the events if the Lambda fails over and over and over? And the answer is probably yes, unless you do a few things. So persistence for the Lambda API, there really isn't one. It'll do 2 retries, and after the 2 retries, it throws the event away, unless you've set up a dead letter queue, which I'll talk about in a minute. SNS will do some retry, up to 13 hours, but then is going to throw it away. SQS is much better, 14 days, and it never throws anything away unless you actively delete it. But SQS has a max depth of 120,000 elements, events. So you can blow the end of your queue and then go 120,000 into the dead letter queue and blow that. So 240,000, and you're starting to lose data. And Kinesis is virtually impossible to lose data in Kinesis, actually. But you do pay for it if you go over 24 hours. Also, retry and failure handling in Lambda, if it's an API call or you've executed it, retry logic is basically done around the invocation. So we have a queue, we'll manage the invocation. And it'll retry twice, and then it'll dump it, unless you have a dead letter queue. SNS does this sort of exponential back-off thing, and it will continue to retry for maybe 13 hours or so, and then it'll dump it. SNS is actually the hardest one here for retries. Getting a spillover mechanism for SNS is actually pretty challenging. You can do it, but it takes some work. SQS is much simpler. They just remain in the queue until you pull them out, until you actively delete them. So assuming you don't hit your max time in the queue and you don't hit your dead letter queue, you don't have to worry about it as much. And Kinesis, again, goes by shard and has a cursor, so you practically never have to worry about retries. The other thing about retries, if you cared about order, let's say it's in SNS, and it's starting to retry, it's not going to retry in order, right? Order is gone because it's going to send them through as soon as it gets them, right? And if you're doing exponential backoff, it may get some newer ones before the older ones. So order will be gone. FIFO queues can keep order on SQS, but most SQS doesn't use FIFO for performance reasons. And so probably order doesn't matter there either. So if order is important to you, think about what retries mean from an ordering perspective, and is your application item potent? So the solution for most of this is dead letter queues on Lambda. If you're not using, how many people have used dead letter queues on Lambda? Very few. Use it on every Lambda. Why wouldn't you? It costs nothing. If the Lambda never fails, it costs you literally nothing. If the Lambda does fail, it saves your bacon. And by the way, it's an SUS queue, which is like 50 cents per million messages or something. You should use it. There's no reason not to use it. And you should instrument a CloudWatch to watch your dead letter queues and tell you when you're starting to spill over into dead letter queues. Because it's not a question of if your function is going to fail at some point. It was going to fail, right? This is the nature of chaos in big systems. So the key is don't lose data and make sure that your retry mechanism works. And dead letter queues are the easiest, cheapest, simplest solution you can imagine. You just turn them on, you put a CloudWatch monitor on it. And the only one here that is a little different, SNS. So SNS doesn't have a dead letter queue. And SNS will just destroy the messages after 13 hours. So one thing you can do is you can have a Lambda that watches an SNS topic, and if any of the elements in that get too old, let's say 10 hours, right, without being addressed, you can send those to another region. You can send those directly to S3. You could just keep a rolling log of all the SNS topics in S3 and just lifecycle those out, delete them every 30 days or something. So solve SNS differently. But for Lambda, SQS, just use dead letter queues. I hate to use the term, but they're dead simple. You just can't go wrong with them. I'll talk briefly about networking. Networking is very confusing for folks. In general, the answer is you don't really want to use VPC ENIs if you can avoid it. And there's three reasons. One is they are performance hogs. So when you put an ENI on your Lambda, it slows down your cold start big time. It's getting better, but you'll take a performance hit. So the way it works is we run Lambda in our VPC. It's a managed service. So when everyone says, oh, I put the Lambda in my VPC, no, you didn't. You put an ENI in your VPC. Like that. The Lambda is still running in our VPC and completely managed by us. The ENI is in your VPC and attached to the Lambda. But the invocation for the Lambda still has to go through the public Lambda API. It's the only way the invocation can happen. So in terms of security, you actually haven't prevented the Lambda from being executed from outside your VPC, right? All you've done is you've given the Lambda access into your VPC to resources in the VPC. So from a security perspective, putting an ENI on it doesn't actually improve the attack surface at all. It hasn't changed one iota. It may have gotten worse because now things inside can hit that ENI. Invocations still come in by the public, and even if you're using a private API gateway, you still won't be able to see, you still have to go through the public internet to invoke the Lambda. So do I need to put it in? The answer is usually no. There are two or three circumstances where you do. So the first one is, if you need access to resources that are only available in the VPC, like a RDS, right? You should put it in the VPC. But then the question is, well, do I put it in a public subnet, private subnet? Where do I put it? If it needs access to a public internet, and remember, public internet includes API calls to AWS, KMS to get a secret, secrets manager, parameter store, right? If yes, then you need to have some natting out to the internet. It doesn't have to be a public subnet, but it has to be natted somehow. If not, if it only needs to talk to RDS, it only needs to talk to things inside, put it in a private subnet. The other scenario is if your company is really concerned with exfiltration. And in this scenario, what you want to do is you want to put it in behind whatever the intruder detection, deep packet inspection appliances are. So if your company really cares about exfiltration and has invested in deep packet inspection, intruder detection, and the security group says every outbound connection has to go through our appliances, then your Lambda will also need, assuming it needs to go out. If it only needs to talk internally, don't put it in a VPC. But if it needs to go out to the internet, it has to go in a VPC. And the other thing about it is, when you use a managed services like Lambda, we manage high availability for you. And we manage IP numbers, IP addresses for you. But if you start using ENIs, you're now marrying your design to our high availability. So if you only give us one AZ, and that AZ goes down, you can't launch the Lambda, because the ENIs can only be launched in that AZ. Similarly, if you give us a /24 like home network CIDR range, and we have 10,000 Lambdas that need to spin up, we're going to run out of IPs instantly. And similarly, if we're sharing it with something else that's auto-scaling, we can nuke, Lambda can easily nuke a Kubernetes cluster, an ECS cluster, auto-scaling EC2 group by sucking up every available IP in the network. And remember, they don't release those, right? They don't release them for 15 minutes. So the key here is, if you're going to do it, always use 2 availability zones. Give Lambdas their own subnets. Network people hate that. And give them big subnets, because they have to be able to have IPs for all the concurrency that you need. If they need to talk to a resource on the internet, you need a NAT. And I know ENIs are pain. We're working on it. Stay tuned. So the last bit is security. Anytime you use an asterisk in an IAM policy, you're making puppies cry. So don't do that. It's an anti-pattern anyway, but it really blows up a privilege. The Lambda permissions model is twofold. The top is the execution policies. What can my Lambda access? And the bottom is what can invoke my Lambda? And they're big, hairy IAM policies. I imagine most of you have struggled with them, been frustrated with them, et cetera. We've put some tooling in to speed that up. Who uses SAM? Okay, if you haven't used SAM, you should look at SAM. SAM takes a few lines of YAML and turns it into many resources in the cloud. And it'll take this policy, for example, an SQS policy, 2 lines of SAM code will blow up into a full-blown IAM policy. And by the way, if you don't use CloudFormation, you don't use SAM, you can still use these policies. We publish them out on the internet. You can go out to the internet and use them. So if you're using Terraform, you can still benefit from that technology, or at least the work that's gone into assigning those. So again, the key points here: more memory, more memory, more memory. Use Xray to understand what's going on. Think about your execution model, and not everything has to be an API. Minimize the scope of your IAM permissions, and try not to use VPC ENIs if you can avoid it. They're really costly. They eat up IP space, and they hit performance. So in closing, there's 2 places you can affect performance. Here, this is your Twitter shot. You want to get a good screenshot from this session. Here are the 2 places you can affect performance. And pretty much beyond that, it's in our hands, and so we're working all the time to improve it. I think also, if you haven't gone to the serverless site on AWS, pay particular attention to the resources button up there in the middle. There's blog posts, there's pair coding on Twitch, there's a ton of resources, and particularly there's a serverless application repository where people just publish their serverless applications, and you can reuse them. So you shouldn't have to code Lambda functions from scratch. I think I won't cover these. So thanks. I will take questions up here. We're about a minute over. I apologize. But thank you very much for your time. Please do a survey.